So in the last lecture, I introduced the concept of it's defined on this so-called combined Hilbert space of two parts, and I just call them A and B. And the definition was very simple, that rho A reduced was nothing but summation, or actually I will write as a trace, it's probably more standard. Trace of B rho A B, where A and B are indices which cover this Hilbert space directions in some sense or the other. This was just the definition, and I described that it has certain nice properties, and that is why we are going to use it. But before I do that, let me repeat some of the standard properties of trace which are part of linear algebra. And what do you mean by trace of a matrix? So we'll just write it as sum of the diagonal elements in some basis. The basis is taken to be orthonormal, so you can think of as a Cartesian components of the vectors. First element is the first one, first Cartesian component 1 and everything else 0, then the second one, etc., etc. So it's this is orthonormal. And one can ask, what basis should I choose? And the answer is, it doesn't matter. Okay, so let's see that explicitly. So construct another set of basis vectors from this by performing general transformation. So this is a vector space, and any general transformation of basic is a unitary transformation, some rotation, whatever it is. So I can write this where I have to put indices, or I can, this is just understood as a whole set. So there are many of these I vectors. I applied a unitary transformation and I will get a new set of vectors. And now I can ask what is the corresponding result of using this basis. So it's very straightforward. In the new basis, this is what I will write as a trace. But then this can be written as J is equal to U times I, and I just plugged it in. And now it is a trace in the I basis, but for a different object. which is trace of u dagger mu. And if you now remember the definition of multiplying the matrices and taking the trace has a standard property that it is cyclic. So I can take the product here and permute it cyclically. I can take u dagger to the other side. U times u dagger becomes equal to identity. So this is equal to trace of M. So the choice of basis actually doesn't matter. So even though the definition might look like that I am choosing some basis and calculating it, the quantity is basis independent. And that is a nice, both are the same thing. If u dagger is equal to identity, u times u dagger is also equal to identity. And a particular definition which is useful that I can choose some matrix which is diagonalized in some particular basis and then I evaluate the trace. So this trace then is just a when I take the diagonal elements, it are going to give me eigenvalues. So it has a nice interpretation, basis independent. That is an important point. And so yes, you can define this, and we saw various properties. I will repeat that trace of row reduced. I have to put the index. Now if I sum over the directions in part A, this is equal to 1 because the original definition of whatever the density matrix is, it had trace 1. I did this thing in two parts, summed over this index first and summed over other index second, doesn't matter, the normalization is preserved. Then the second thing which I mentioned is this expectation value of some operator which acts only on one part of the system and don't have any control over the rest of it, and you don't do anything to the other part. What will this look like? So this is by definition in the large space, the expectation value of this object, and since nothing depends on B part is trivial, and trace of row AB becomes a reduced matrix, so this becomes a trace of row A reduced times OA, where this trace is only on the part A. I just summed over all the indices B, nothing happens here, and this becomes a reduced matrix. So this is as if I am only looking at one part of the system and using the standard rules of calculating the expectation value. Whatever operator I am using it is fine, and the corresponding density matrix. So these are all simple properties. So what happens if I evolve the matrix or the system? So there the general rule was a unitary transformation on the density matrix in the original part. So now let me choose the same kind of structure, that I perform some transformation on the part A, don't do anything on the other. Okay. So I plug it in the whole evolution of what happens to the reduced density matrix after the transformation. Okay. So that will be given by trace B, then U A cross IB times rho AB times this is the reduced density matrix. After the transformation, I just plugged in this rule in the whole system. Again, I can use the property that IB is not doing anything. So I can take this B trace rather trivially. And U and U dagger are acting only on the part A. So this will look like UA rho A reduced times UA dagger. It's the same evolution rule as this, but as if the other part is absent. So this is again property where you don't make any reference to whatever happens on the B part, it's just ignored, you are not doing anything on it. And then the last property, which is used for defining the density matrix. So we have the normalization, we have the measurement, we have the evolution, and the property which remains is positivity. Does it satisfy? So the definition which I pointed out for any psi in the joint space this holds. But this is again some contraction of the density matrix. I can take the component of psi in the B part to be trivial. Okay. and then that will be a contraction which will just produce a trace on the part B, because these are the same indices on both sides, and the result is that I will have a result which is rho A reduced this is positive for all states psi A by just making a choice for psi AB where B part is trivial, and then this gets summed up to this trace, and the A part remains whatever you want. So this property is kind of assure that I can treat this reduced density matrix in the same way as I was using the ordinary rules of quantum mechanics. Doesn't matter that it describes only the part of the system, it has all the property, normalization, expectation value, evolution, and positivity. The only difference is that the positivity doesn't give you the result that the reduced density matrix is pure. It just tells you that the eigenvalues are some numbers between 0 and 1. While the initial state in the large space could be pure, where the eigenvalues of the rho AB would be only 1 or 0. That doesn't necessarily hold for the reduced density matrix. So rho A reduced, or rather obeys all quantum axioms it need not be pure. In general, it is mixed. So this gives a powerful handle that even if you don't have any control over part of the system, you can do the usual manipulation of the quantum theory on the part on which you have control. With the caveat that at the most you will be dealing with a mixed state. Doesn't have to be pure. Yeah. Yeah.
But like the evolution of the system like A and B, if we talk in terms of the like open system,
Yes.
like it's coupled with the environment, then also we can do something like that.
Yeah, that is exactly the point, that you can manipulate the system which is under control and don't do anything about the degrees of freedom in the environment over which you have no control. And I'm implicitly writing it that this is transformed, the environment is whatever it is. It's identity operator.
They won't impact on the system, but the system B will have some impact on the system.
It can have, but the rules are still the same. They are connected. We'll see that they are connected, but the whole formalism, the importance of it is that you can still treat it as if the other degrees of freedom can be ignored. Because of the connection, that is what makes a pure state to a mixed state. Things happen, but you can apply the rules of quantum mechanics. That is the point. So this is a constructive picture that You started with certain definitions and axioms and defined the reduced density matrix and worked out all its properties, which are nice. But mathematicians also ask, is there any other construction possible? Or in the sense, is this unique? More generally, you can call some conditions as necessary and some conditions as sufficient. So what I have done here is the sufficient part, that okay, this scheme works. But there is a powerful theorem which I'm not going to prove, but it's important to know, which shows that this is also necessary. And then the job is over. This is the only formalism which you can use for describing quantum system obeying certain rules. So what is that counter statement? Okay. What do we actually see in the experiment? That the quantum system gives you certain answers with certain probabilities. You don't know its dynamics, you have to cook up the Hamiltonian or the Schrodinger equation if you want to do the dynamics, but that is not showing up on the instrument reading. You only have certain rules, and now you make very simple assumptions about what these probabilistic situations could be, and it tells you that the only choice you have is to construct the density matrix. Okay, that is a counter statement. So what do you expect the probabilistic rule to be? Well, very simple things, that choose an independent set of measurement results, and these measurement results are classical because they show up on our instrument, and when I say it is independent, that means they are disjoint. If I measure one value, the other value is completely separate from them. There is no possibility of superposition and that kind of mixing that doesn't appear on the apparatus. So and Gleason assumed three criterion. So let me call this some value which I call Mi. So one assumption was that the probability of no measurement is equal to 0. Empty set, you are not counting any of the possibility at all. Kind of trivial. The probability of all measurements, so which means sigma I over mi, this is equal to 1. Count the probability of all possibility, it is 1. These are kind of trivial thing. By definition of probability, you want to have such a thing. The third assumption is crucial, and it says that probability of mi and mj, so it's a union, okay. Two possibilities inside here is equal to probability of mi plus probability of mj for I not equal to j. That if the two events are disjoint, as I assumed, the probabilities add. This is a kind of expected behavior of the probability in classical physics. And the conclusion is that any such set of observation can be written in the language of density matrix, where the probability is nothing but projection of the density matrix. This is what the trace involves, and pi is some set of vectors associated with this direction I. This is exactly what was summed over here to make that object trace, the total trace becomes equal to 1. So this is a powerful statement. It says that this is what you see on the observation on the instrument. There must be a theory where all these probabilities are described in terms of a density matrix. No other choice. And that kind of completes the story that the density matrix is the most general description you can make about a quantum state, necessary and sufficient. Okay. So let me now, I can write this object in a separate way, that pi are disjoint operators. This Kronecker delta gives that particular statement, and we also have the whole thing sums up to identity, and of course these two statements are then become kind of trivial, and disjointness is guaranteed by this, that if I sum over pi and pj, well, I will get one contribution which is pi, the other contribution which is pj, and satisfactory result follows. And Yeah, there is one caveat I have to mention, that this the theorem gives unique row for dimension greater than 2. That means there is how many possibilities are there for I?
Sir,
Yeah.
if we put I equal to then that is PI here, is PI times one other, then we get PI square is PI will be identity of the matrix.
Pi square equal to Pi is fine. That just is a trivial statement coming from that. It's a projection operator. Definition satisfies that Pi square equal to Pi. If you project twice, you don't get anything more. It's the same number you will get. So why this condition appears? That yes, you need a Hilbert space of dimension bigger than 3, but if you have just dimension equal to 2, which is what you have for a qubit, this solution still remains valid, but there are many solutions. And actually, infinitely many. If you try to work it out, and the reason is because there are not enough independent directions available. And in the language here, the third statement collapses. The reason being that it's a two-dimensional space, and I and j, I not equal to j cover both the possibilities, and the second axiom already tells you what the answer is, it is 1. I don't have a new variable. Okay. Probably what I was writing, M1. While for any larger values, there are many possibilities to construct this union by choosing different M1 and M2, whatever it is. And that gives you a flexibility which constrains this unique answer. Here that answer is still there. I mean, whatever the density matrix gives you is a valid answer, but you can construct many other infinitely many other answers. And if you try to think about a density matrix of a qubit, you will be able to see that yes, there are lots of possibilities which can still describe this probability of 1 and 0, they add up to 1, some sense. So this is something which is worth realizing that yes, the density matrix which we have introduced axiomatically is also kind of forced onto us by just this simple looking probability rules, and you don't have to refer to any axioms of quantum mechanics. It has to be of this particular type. And then you can ask, what about classical mechanics? Well, the same assumptions are there in classical mechanics, except that you don't have to do all the jugglery of a matrix because the life becomes much more easier. In classical physics, it's just a diagonal density matrix. So diagonal matrix, you don't have to treat as a matrix. They are just diagonal elements, which are the probabilities, and they are all disjoint and they add up to 1. It's a very simple situation. Quantum mechanics gives you more complicated structure, but even in that case, you cannot go beyond this particular definition of the probabilities.
So, what about like many types?
Yeah.
It's like we represent in different bases.
You can have the definition of probability. This is one definition. But you can construct other definitions which will obey the same rules.
So we can like create different projects.
Rho will be replaced by something else. Doesn't even have to be a matrix. Some algebraic expression of constructing the probability. In terms of whatever the projection operators will remain because they label the directions you are measuring. But there will be some function of the projection operator which will give you the probability. It will not have this particular form. Okay. So now I can go to a powerful theorem which is known as the Schmidt decomposition, and is referred to bipartite system of the same structure, some Hilbert space A and some Hilbert space B. And what follows is a just implication of this algebra, nothing more than that. But it's a very useful result and something worth remembering that this result was present in linear algebra before quantum mechanics came along. Okay, so it doesn't have to do anything with quantum mechanics. It was true and it was borrowed for practical applications in quantum mechanics. And what it does is it allows you to write some joint state in this total Hilbert space in a expressed in a simple manner. So the derivation will get over in some 2-3 lines, but just pay attention to the logic because that is important. So I start with some general state, okay? And I can always write it in this. Well, let me put this indices explicitly. So I call this, one of them is a Roman letter, the other one is a Greek letter. So this is some orthonormal basis, this is some other orthonormal basis. The total space is covered by IA for the first half and the mu B by the second half. This is a total general description summed over all I and all mu, which cover this basis. So these are orthonormal. This is always allowed. Now I define something auxiliary, which is just some notation. So I take a sum over mu separate and sum up everything which depends on mu. This is from the coefficient and this is from the vector. And it's always possible. And whatever comes out, it has only one index left, which is IB. It is linear algebra, so it is some combination of these basis vectors, and it produces some other vector in that same space. It's in the B space. And if I do that, then some combination with some coefficients, this state is not orthonormal or normalized or anything, it's just some vector in that space. That's all I can say. But now I can write this thing as a sum over a single index. I just redefine something and that is all there is left. But this has a very nice feeling that yes, there are some set of vectors I in the first half and corresponding vectors I bar in the second half, and I just summed over those particular possibilities. So far what I have done is a kind of identity, so tautology, nothing used. Now I am going to choose the first half that it will diagonalize the reduced density matrix corresponding to system A. This is the crucial step. What does it tell you? Well, for that I have to work out what is the reduced density matrix. But I have the definition of psi AB, and all I have to do is to take a trace. So let me do that. What is okay, so there is one way of expressing this result. Let me write it explicitly before I do the other half. So what does the diagonal matrix means? That rho A reduced is equal to sum over the diagonal elements, and diagonal elements, whatever they are, they add up to 1. The trace of this thing is equal to 1. Okay. So here it was just a general. Now I am saying that whatever I am choosing, it's special so that it obeys this result. Always allowed, because this is a Hermitian matrix. It will have some basis where it will be diagonalized, and it will have some eigenvalues which add up to 1. No problem with that. But now I can obtain this starting from this expression. Okay, here is just a definition. So what is rho A reduced? Is equal to trace over B of this stuff trace B is actually just a sum over mu, but okay, let me just write it more explicitly. I have to write all the coefficients, or I will just write it in this language. So I took this particular form, and the density matrix is the outer product of this with itself. So this is a outer product. I is a cat. This is the bra, and to avoid confusion, both of them have sums. One sum I called I, another sum I called J. But now I can take the trace, because this B index is there on these vectors. Take the cyclical result, so it will create an overlap of I bar with J bar. nothing happens to I and j, there is no trace over it. The trace is the one which gets permuted and produces this number. So now we have two different expressions. Both of them are written in an orthonormal basis, I and j. And they have to be equal. There is no other choice. And when are they equal? Well, you look at component by component. There are all kind of off-diagonal stuff inside sitting over here. That all has to be 0. So these two match when there is no other choice because it's an orthonormal set. And this tells you that j bar and I bar, even if you didn't assume anything, they are already orthogonal. And on top of that, I can absorb this normalization. So if I define something like pi raised to minus half I a ib there is some normalization stuck over here, but I can take a square root and stick it in front.
We started with I and j to be orthonormal. And how did this pi come in?
No, I have this rule. So I define some object, let me call I, B. Now how do you define it? Let me call it prime. IB prime is equal to this negative half square root times IB bar. If I now construct this j prime and I prime, I will only get delta ij. Okay. So I found a new basis in the system B by all this convoluted stuff. Some coefficients got buried inside it, but whatever it is, I could construct an orthonormal basis. And the result of all this thing is, look at now what this I just substituted in this, nothing more than that. So look at what happened. We had a generic sum over two indices. It has been reduced to sum over only one index. Both these bases are orthonormal. One is in state space A, another is in space B. And there are some weights in front. They are governed by this rule. There are all some numbers, or positive numbers describing some probabilities. And this is a great simplification because you had a double sum which somehow you have managed to collapse to a single sum. It's possible due to a clever choice of basis. And what was the choice of basis? That it diagonalized the reduced density matrix. You can look at it in different ways. After doing all this jugglery, the expression looks symmetrical in A and B. So you can ask, what is IB prime? Well, you can say that it is the basis which diagonalizes row B, the reduced version. Interpret it either way.
So if the Hilbert spaces are different dimensions,
Yeah,
we'll have the summation across the lower of the summation.
yeah. So now there are a whole lot of consequences which follow from this. And that is what makes this result very powerful. I can write down some of them. But before I do that, let me point out one interesting stuff that I have not assumed anything beyond linear algebra, that some matrices are there are some coefficients, and you do the standard stuff of diagonalizing the matrix, and you'll end up with this particular result. But there is a important property which is buried inside this linear algebra arguments, and that is, this is possible in a Hilbert space with complex numbers. If you say that I am going to just work with a vector space of real numbers, you cannot derive this result. And it's kind of implicit, but I want to emphasize it, so just for sake of clarity, and that is, even if you take matrices which are all real, when you try to diagonalize or perform these transformations of change of basis from rotating from one basis to another, you end up with complex numbers, whether you like it or not. And a simple example is suppose I just work with a two-dimensional space and I have some x and y coordinates. I want to rotate it, so some x prime and y prime. I can write x prime is some real number, x prime, y prime is some real number. Even the transformation matrix is also a real number. So where do I need complex number? Okay, so let me just two-dimensional rotation, change of basis. And this is a familiar matrix which you have probably seen many times. Just made up of cosine theta and sine theta. If I take some axis, rotate it to a new axis, what is the transformation? And it gives the coordinates. All the coordinates are real. But what are the eigenvalues of these matrices? Determinant is 1. So the eigenvalues have to, well, there are only 2 eigenvalues. They have to multiply to 1, and trace is 2 cosine theta. So the eigenvalues have to add up to 1 or 2 cosine theta. So this has complex eigenvalues. So whether you are like it or not, just playing with real numbers and very trivial rotations you perform, you'll end up with the complex numbers. And if these things are not there, then of course the arguments which went inside there, I can rotate, I can diagonalize the matrix, they will all fail. They cannot happen within just space of real numbers. And that is why this decomposition there, but it is in the Hilbert space with complex numbers. It doesn't work if you have only real numbers. And of course, eigenvalues are complex, and eigenvectors, if you calculate, they will be also become complex. So this is an elementary fact, yes.
Just there is a active quantum parallelism because the summation of two indices has reduced to the one indices. So does this tell us anything about the parallelism?
Not the parallelism. I'm going to work out several consequences, but I wanted to point out this thing first because the arguments can be quite straightforward, but what is buried inside it is requires some attention. That yes, you are doing this, but you must have certain possibilities for defining all these vectors, otherwise it would not work. So if you say that the Schmidt decomposition, does it work in a real vector space? It doesn't. You need complex numbers and then it works. So now let us look at this expression. I did not assume anything about the dimensionality of the two systems. Okay, it was just fairly general. So So how can then this kind of expression hold? The only way it can hold is lots of terms in this summation are 0. The possibility of what is over here and here can be very different because there is no relation about this dimensionality of space. Well, you have lots of other stuff, make all this other part equal to 0. So there is number of non-zero pi, because then those are the terms which will contribute to the sum. Everything else is going to disappear because it's 0 is called the Schmidt rank. The usual rank is the definition connected with properties of linear algebra, and let me call it RS. And it's smaller than the minimum value of all these things. If R is equal to 1, that means there is only one term in this particular summation, so the state factorizes. Because something in A and something in B, there is a tensor product between the two. But now comes a definition which is rigorous about the word which I have used before. This is a state is entangled. So this is a rigorous definition of what entangled means. If a Schmidt rank of the joint system is larger than 1, there will be at least 2 terms in this particular summation, and the combination will such that you will not be able to factorize it in any way. These are all orthogonal coordinate systems, and whenever that happens, you call the state entangled. You can define magnitude of entanglement also if you know these values of pi, but that's a different story. But this is the first statement. Similar thing, you can say that how many components are entangled. The number of components which can be entangled is smaller than the dimensionality of either of the spaces. And that means you can take one small system and then the rest of the world, the whole environment. Most of the environment just doesn't matter. The number of components which matter in the environment are the same as the number of components of the system. It cannot ever exceed that. And all that we don't know is what are those components in the environment. We have no clue. But we know that they are as many as the number of components in the system. Cannot be anything more. And well, in practical situation, that means if you figure out what those other components are, you can ignore the rest of the environment. And a lot of the exercise in terms of developing good hardware focuses on that. Can you figure out the environmental components which get entangled with the system? They are finite in number, described by the size of a system. If it is a qubit, there are only two components of the environment which couple to it, nothing more. And if you figure out those two, then you can control the whole thing much better than when you didn't have any knowledge at all. The hardware challenge is to figure out what those two components are. Okay. So, and the relation is that you want to describe a complicated general system. You have some dimension over here. Well, only the same number of dimension over there is going to contribute, and then at the most you have to keep track of dimension h square degrees of freedom. Nothing more than that. If you have a qubit, well, keep track of 4 degrees of freedom, and that will be all that you will need to describe the most general interaction. And there is essentially it's a one-to-one map between IA and IB. And it has been given a name which you probably see somewhere in reading about this topic. It's called monogamy. Many of these words are consequence of who wrote the first paper describing it. They invented some adjectives, and well, we are stuck with them. Fine, I need to erase something. Let me. Anybody want to take a picture? Just take ahead before whatever it is. Huh?
Which part you want me to erase?
You take a picture first, and then I will erase somewhere. Like I will erase this part. So now I can look at this expression and ask, it has all this nice structure, but is it unique? And the answer is no. For the simple reason that all we landed up with is an orthonormal basis over here. I can rotate this orthonormal basis independently on some another orthonormal basis, and it will look the same state in the new basis. No problem. In fact, you can make a more general statement. This is one orthonormal basis. This is another orthonormal basis. It's a one-to-one map. And the non-zero components have the same length. As a matter of fact, you can choose or rather select that IB prime is nothing but a unitary rotation of IA. Same dimensional space, two orthonormal bases, they can always be related. So again, simple consequence, but the statements, the first time you see them, look little surprising, but there is nothing complicated in them.
So for that to happen, both the element space should be of same dimension.
Yeah, because it's a one-to-one map. Everything else is coming with this coefficient equal to 0, just ignore them and look at only the non-zero terms.
Can be rotated independently by unitary transformation. It's different type of unitary transformation. G1 unitary transformation rotate IA and GOV unitary transformation rotate I.
Yeah, if I apply unitary transformation, I will just go to a new basis, but this factorization will remain true. That IA will be replaced by some unitary transformation acting on IA. It will give some components, but the structure will remain the same. If you want to write it in a different way, that some unitary transformation on space A and another unitary transformation UB I apply to this particular states, it just will just lead to a new definition of what you mean by IA and IB. Because it's a coordinate system. You can rotate the basis. The both fact that this is a tensor product means if you are factorized, I can independently rotate IA and IB in whatever way you want. And the last thing which I want to mention is actually the most powerful of all this result, and that is I take arbitrary rho A reduced. This form. It can be extended to this language, which is a pure state, by adding dummy components in the environment. How many components you need to add? Well, it's already fixed. How many numbers of non-zero eigenvalues are there?
This psi AB is the pure state. This psi AB is the pure state.
By definition, yes. This is a vector in the Hilbert space. Reduced density matrix is not a vector in the Hilbert space. Number of non-zero eigenvalues of the reduced density matrix. And this means that what came from the Gleason's theorem, everything could be described by a reduced density matrix. In general, I add a few more components and then everything will be described by a pure state. Works in reverse, but it's always possible, so there is no loss of generality in taking the I have some system under my control. Figured it out, it obeys some reduced density matrix. I can always construct a universe by adding new components, and the universe always works with pure states. There is no loss of generality at all. And this is the most powerful consequence if you want to use the quantum mechanical axioms. Yes, you can take any complicated situation and find an equivalent setting where everything is described in terms of vectors in Hilbert space, where you can do all kinds of things, superposition, interference, without ever worrying about that reduced density matrix. So I will stop here, but this is the stuff which is extremely useful in lots of different settings. In particular, what are known as error correction schemes. You are working with something, all kind of disturbances happened with the environment, but you can assume that the system plus environment is a pure state, perform some transformation which corrects the errors by rotating it back, and then you again have a pure state. So there is a whole machinery about how to correct errors in quantum theory, which is based on this particular property. It's only a simple consequence of working with bipartite systems, but it allows you to do all those things. So when you are doing error correction, you never worry about all the mixed states and reduced density matrix. You assume that the system plus environment is in a pure state and do the calculation. There are more consequences, but I will stop at this stage.